Alright everybody, welcome back. In this video we're going to discuss information from section 4 of Unit 2 of AP Calculus, connecting differentiability and continuity, determining when derivatives do and do not exist. Okay, so first, we're talking about this new idea of differentiability. We already should know what continuity is, but we're talking about this new idea of differentiability. So what is differentiability, first of all? I mention it here in a parenthetical comment. Can we find the derivative of a function? If we can, it's differentiable. If we can't, it's not. So if we can find the derivative of a function at a point, it's differentiable at that point. Okay? And we see that right here. A function f is differentiable at a point a if a is in the domain of f prime. In other words, if f has a derivative at a, it is differentiable at that point. So let's tighten that down a little bit. In order for a function to be differentiable at a point x equals a, we need two things to happen, and this should, remind you a little bit of our definition for continuity, where we required f of a to exist and the limit as x approaches a of the function to exist and for them to be the same. This is similar to that, not identical, but similar. First of all, we need the function to be defined at x equals a in order for it to be differentiable, okay? And it has to be continuous. So that's our first statement here. F of a has to be defined, and it has to be continuous in order for it to be differentiable at that point. And then what we need, and this should look familiar to you, this is the limit as x approaches a from the right of our difference quotient, and the limit as x approaches a from the left of our difference quotient. Now realize, again, the limit as x approaches a of these difference quotients are finding the derivative of the function f of x. And so this is basically saying the left-hand derivative, or the derivative from the left-hand side, has to be equal to the right-hand derivative. Kind of like when we talked about the left-hand limit and the right-hand limit having to be equal to one another in order for the limit to exist. Now it's the left-hand derivative and the right-hand derivative that have to be equal to one another in order for the derivative to exist. Next statement that I make here, a function that's differentiable at every point of its domain is what's known as a differentiable function, just like a function that's continuous at every point of its domain is known as a continuous function. And, back when we first did continuity, we came up with kind of the layman's thought process, can I draw this function without lifting my pencil off the paper? When it comes to differentiability, kind of the layman's process is, we usually think about them as smooth curves. There's one notable exception where there's a type of smooth curve that is not differentiable, and we'll talk about that later on in this lesson. We might get to that this video, but maybe not. All right, let's look at our first example. Determine if the function y equals f of x is differentiable at all values of x. Okay, so since this is a piecewise function, we saw this with our ideas of continuity. Let's first look at one piece, then we'll look at the other piece, and then we'll see about where the pieces meet. So let's focus first on this upper branch, f of x equals x squared plus 1 for x less than 1. Imagine what the function f of x equals x squared plus 1 looks like. Okay? Does the derivative, or the slope of the curve, approach the same value from the left and the right for all the points on this curve? And it does. So I know that this is differentiable for x less than 1 because for all x less than 1, left and right-hand derivatives are the same. and we don't really need to imagine it. We can, if I step up here, here's my curve, y equals x squared plus 1, and we're really only focusing on it for x values less than 1. But if you look at the curve everywhere, if I pick any point on this curve, suppose I pick this point right here. If I pick any point on this curve, like this one right here, is the derivative from the left the same as the derivative from the right? In other words, is the slope approaching the same value from the left as it is from the right? And it is apparent that it is, and hence the statement that we made here to start. All right. It is also differentiable for x greater than or equal to 1, because for all x greater than or equal to 1, the left and right hand derivatives are the same. And this one's even easier to see, I think, than the first one. If we look at the curve y equals 2x and pick any point on that curve, the slope coming from the left and the slope coming from the right are the same. Of course, the slope is the same everywhere. So the key point for us here, we've now shown that it's, or at least explained that it's differentiable for everywhere except for where these two pieces meet at x equals 1. Okay? So what we need to do is we need to determine whether or not this is differentiable at x equals 1. Well, let's start. In order for it to be differentiable, we need it to exist and be continuous. Okay, so f of 1, that's this branch. F of 1 is defined. And then if I take the limit as x goes to 1 from the left, that's equal to 2. And the limit as x goes to 1 from the right, that's equal to 2. Okay, so f of x is continuous. Now we just need to show that at x equals 1, the limit as x approaches 1 from the right and the limit as x approaches 1 from the left both approach this same value. Okay, so we're going to take the limit. Let me cordon off some workspace for myself here. We're going to take the limit as x approaches 1 from the left of, and now for that branch we're going to use this piece of the function. So the limit as x approaches 1 of f of x minus f of a, which is going to be 2, all over x minus a. It's the limit as x approaches 1 from the left of x squared minus 1 over x minus 1. If I try to take this limit via substitution, it becomes the indeterminate form 0 over 0. So I'm going to factor. And so that's equal to the limit as x goes to 1 from the left of the quantity x plus 1, which is going to be 2. So the limit from the left is 2. The limit from the right, now for the right hand we need to use this branch, and so we've got f of x minus f of a all over x minus a. Again, if we try to handle this via substitution, it turns into 0 over 0. So I've got to factor and cancel. Okay. And so f of a is defined and continuous. And the limit as x goes to a from the left of the difference quotient is equal to the limit as x goes to a from the right of the difference quotient. For a equals 1, therefore, f of x is differentiable for all values of x. Okay, let's call it quits there for this video. We'll come back next time and look at types of non-differentiability and some other examples. Okay, so come join us in video 2. Have a great rest of your day, everybody, and we'll see you next time.